Let's talk about probability, which is the likelihood of something happening. Okay, so the theoretical probability of something happening, of an event, is the number of ways the thing you want to happen can happen divided by the total number of ways or the total number of outcomes that are possible. Okay, so for example, flipping a coin, um, if I want to get heads, that's one outcome out of two possibilities, heads or tails. Now, the experimental probability of an event is what actually happens when you uh, do the event and see what happens. It might not be the same as what the theoretical probability is. And to find the probability of multiple events, we just multiply their individual probabilities together. So let's do some examples here. So first of all, and this is what I just said, flipping a coin and getting heads. So the number of ways I can get heads is 1. There's one side of the coin is heads, and there are two possible outcomes there, heads or tails. Rolling a die, a d6, six-sided die, and getting a 3. Well, there's 1 3 on a d6, and there are 6 possible outcomes, so 1 out of 6. Randomly guessing someone's birth month. Well, the desired outcome there is the single month they were born, and there are 12 options. So you got a 1 in 12 chance of guessing someone's birth month. Rolling a die, a d6, and getting an even number. So the total number of desired outcomes here are even numbers, 2, 4, and 6. There's 3 even numbers on a d6 out of the 6 possibilities. Now we can reduce this to 1/2, but you don't always have to. Sometimes it's nice to see the unreduced fraction just so you can see what your total numbers of outcomes were. But reducing it is proper. There's a 1 in 2 chance. Being dealt 4 aces in a card game. This is a little trickier. And for this example, we're going to assume you're getting dealt these cards one at a time, one after the other. There's nobody else getting dealt cards in between. So a regular deck of cards has 52 cards in it. And there are 4 aces. So our probability of getting dealt 1 ace is 4 out of 52. Now the probability of getting dealt that second ace is 3 out of 51 because there's 3 aces left and there's 51 cards left. Likewise, for the third one, it's 2 out of 50 and then 1 out of 49. So we'll need to do a little multiplying here. On the top, we get 4 times 3 times 2 times 1. That's 24. But on the bottom, we're going to do 52 times 51 times 50 times 49. And we end up with 6,497,400. We could reduce that, but because the number's so big, it's going to take a long time to do, and it's not necessary, so we'll leave it like that. Pretty unlikely, but it does happen. Okay, rolling a die, a d6, 3 times and getting 3 sixes. So the probability of getting the first 6 is 1 out of 6. Now, rolling a 6 the first time doesn't change how many options there are. So with the cards, once I'm dealt a card, there's fewer cards in the deck remaining. But with a dice, with a die, it doesn't work the same way. So all 3 of these are 1/6. So our total probability is 1 over 216. So you have a 1 in 216 chance of rolling a die 3 times and getting a 6 3 times in a row. Okay, example F says a bag contains 12 red marbles, 9 blue marbles, 11 yellow marbles, and 8 green marbles. 3 marbles are randomly drawn from the bag one at a time and not replaced. Find the probability of drawing a red marble, then a blue marble, then a green marble. So first, let's count up how many marbles there are. 12 plus 9 plus 11 plus 8, that's 40 marbles. Now, I'm going to first draw a red marble. there are 12 red marbles, so that's 12 out of 40. But now I've drawn a red marble and I'm not replacing it. So now I want to draw a blue marble. There are 9 blue marbles, but there's only 39 marbles left in the bag. Next, I want to draw a green marble. There's 8, but there's only 38 marbles left in the bag. So my overall probability here, 12 times 9 times 8, I get 864. 40 times 39 times 38, 59,280. And again, we could reduce this fraction. I don't see a need to right now, but we could. I'm going to leave it just like that, though. That's okay. 864 chances out of 59,280. Oftentimes with probability, we like to, especially the way we think of things, we like to think of what it would be with 1 on top, right? We have a 1 out of however many chances to get this. So this isn't always a whole number, though. If I divide this number, 59,280 by 864, I get 68.611111, right? So I have a 1 in 68.6 chance of getting it. And this is an okay way to think about this. It kind of helps ground your chances. If you think, okay, I have a 1 in 69 shot. This one up here, for example, E, would have been, I need to clear that first, 6,497, 400 divided by 24. That'd be a 1. Now that one does divide evenly. A 1 in 270,725. So not very likely, but a little easier to understand than the 24 out of 6 million something. You know, you think of a 1 out of 270,000 shot. That makes a little bit more sense. Just mentally. Okay, Candace drew a card from a regular deck of cards, recorded the receipt, replaced the card, and shuffled the deck. She repeated this process 100 times. Her results are shown in the table. So hearts 32, diamonds 19, spades 11, clubs 38. Find the difference between the theoretical probability and her experimental probability of drawing each suit. So the theoretical probability of each of these is 1 out of 4. There's 4 suits. And we can change that to 100. Theoretical probability is 25 out of 100 for each one. So for hearts, and we're find the difference between the theoretical and the experimental. So 25 out of 100 minus 32 out of 100. We'll call that a negative, but it doesn't really matter. We're just finding the difference here. Negative 7 out of 100. So she drew 7 more than expected. We'll just call that, we'll just do a positive here. For diamonds, we have 19. So 25 minus 19. We'll say plus on this one. She was more than expected there. She drew more than 25. For diamonds, 25 minus 19 is 6. So she was down 6 from where she expected to be. For spades, only 11, so 25 minus 11. We got 14. She was down 14 out of 100 from expected. But that's theoretical probability versus experimental. Right? You're not going to get exactly the same as your theoretical, typically. 38. So we're finding the difference here, 25. Should have done 38 minus 25, I guess. We get 13. She was 13 out of 100 more than expected there. Okay, so not exactly the same as her theoretical probability, but that's okay. That was her experiment. All right, last one here. 4,000 people participated in a study to determine the effectiveness of a new medicine. The results are summarized in the table shown. What is the probability that the test subject remained healthy given that he or she used the experimental drug? So we'll do this one first. And then what's the probability of remaining healthy if given a placebo? So for the drug, probability that the test subject remained healthy given that he or she used the experimental drug. So using the experimental drug is this column here. Looks like there were 2,400 test subjects who used the drug, and 800 remained healthy. So an 8 out of 24, or a 4 out of 12, or a 2 out of 6, or a 1 in 3 chance of remaining healthy if using the experimental drug. For the placebo, which is a sort of a mental trick, right? You're given a pill, usually it's a sugar pill, but it doesn't have any medicine in it. And so it's seeing whether the drug is effective or if it's just a kind of a psychological effect. So for the placebo, there were 1,600 test subjects, and 400 remained healthy. And this does divide evenly as well. 4 out of 16 is 1 out of 4. So your chances were a little bit better with the actual medicine here, but not that much better. Okay, so there you have probability. In general, it's the number of desired outcomes over the number of total possible.